from the last speaker. So in Danish we call the one to finish something raisin in the end of the sausage. I don't know where that comes from, but I'm the raisin in the end of the sausage in this conference. So I'll try to seeing that we're ending. I'll try to keep things as light on detail as possible. So the goal is to we want to parameterize representations of a three-manifold group. Let me just state it generally. So G is just some Lie group symbol. And M is a compact three-manifold. So what we want to do is we want to give some variety that computes the points of the set of representations. So it's very easy to convince yourself at least that you have simple groups like SLM and stuff that this group should give a variety because this is just finitely generated. So you just give some, if it's a matrix group, you give some matrices to each generator and then the relations will give you relations among the entries. So it's very clear that there's some kind of variety. But this is, of course, if you try to do any computations with that, that's impossible. You can't get anywhere with that. So we want to have parametrizations that are nice and have some nice structure. And we also want it to be such that invariants that we're interested in are easy to compute. So let me just say what the invariants are that we're interested in. So what are invariants of a representation? We have some classical invariants like volume. So let me state how it's defined. So you have a representation into G. So such a representation, it has a developing map from the universal cover of M into this space, the case of maximal compact subgroup. This is just because such a representation is equivalent to a bundle, and then the associated G mod K bundle, since this is a contractible space. It has a section, and sections are in one-to-one correspondence with these gadgets. So there's a map there, well defined up to homotopy. It's equivariant with respect to this. And so G mod K has a canonical freeform. Let's just call it omega. And what you do is you define the volume of a representation. Let's call this the definition. What you do is you take the free form there and pull it back. And then you integrate it over some more fundamental domain for M inside that filter there. And so why do we call this volume in general? If G is just any Lie group, any complex Lie group, it's not at all volume in any usual sense of the word. But as we shall see, it's actually something that has some mysterious relationship to volume. And if you use a Lie group SL2C, you can see that it actually is volume. So let's just give an example. So for example, if G equals SL2C, then G mod K, the maximum compact subgroup, is SU2. So this is this hyperbolic free space, and this omega is the hyperbolic volume form. So, and then it's not so. If you have the geometric representation of a hyperbolic manifold, this map is just an isometry. It's a developing map, and then it's not then if you integrate the volume form over the fundamental domain, you just get the volume. So here if n is hyperbolic, and rho is just the geometric representation, let's say the volume of the geometric representation, this is the volume of the manifold. So in this case, it really is volume. But there could be lots of other representation, even if you start with a hyperbolic manifold. And it's not at all clear that they have anything to do with hyperbolic volume. But it turns out that it is somehow related, although in a mysterious way. So we can just call this volume. It's in SL2, it is that sensitive volume. And so there's also, I should just say, there's also, you can generalize it to a complex valued invariant, which is called complex volume. There's also have complex volume. So volume here, this is some real number. And so this is C. And this is some complex number, where the imaginary part is only defined up to and for the complex volume is the invariant that's already been mentioned, the volume of the function Simons. So that's somehow classical invariance, and there's other invariants that we're interested in. So what we want is we want to parameterize representation, give some variety with explicit coordinates that are explicitly computable, so that we can write down explicit formulas for this. So that we can do, I should say, somewhere after I should credit Coauthors at some point. This is going with Stavros, Garoufalidis, and Matthias Goerner, and Thurston. And this is in two distinct papers. One with Garoufalidis and Goerner, and one with Thurston. So this is not Thurston. And the explicit computations that we're using, they are they due to software that's been implemented by Matthias Goerner. So he now works at Pixar. Okay, so there are also quantum invariants. I'm not going to say too much about them, just a little bit as a kind of teaser of why it is that we're interested in these representations and what it is that we can do with them. So we have the volume conjecture that says that if K is a knot, hyperbolic. Let's define M to be the complement. So basically, you can phrase it as the Collar-Jones polynomial. That this goes as, so let's see if I can get this right. So the original version says that it grows asymptotically, and the growth rate should be equal to the volume, or more generally the complex volume. But there are generalized versions that also says something about subleading terms. So this is, I'm gonna find each part. So how does it go? This is the complex volume. And then some logarithmic term, which I don't remember, and then some power series. So this is something like S1 plus S2 h bar plus h3 h bar squared, something like that. And these invariants I call loop invariants. You can also call this, maybe there's an I, doesn't matter. Call that S0. So Si, that complex numbers, I call loop invariants. I guess S0 is. I think these are well-defined complex numbers, but S0 is only defined by pi squared C or something like that. Okay, so what else do I want to say about this? Yeah, and there are also various versions for representations. So there's also a volume conjecture for if you look in representation space, deform the geometric representation or hyperbolic manifold a little bit, then you will get the complex volume of that representation. You will have different values of these, and it will be called a Jones polynomial evaluated not at a root of unity, but in some neighborhood of root of unity.
And the SI are in the invariant trace field.
Yeah, that's also conjecture. Yeah, they will be in the invariant trace field. Also conjecture. They're actually in invariant trace field. So all this is conjectural, so we might as well conjecture that as well, because that's what will follow from the explicit formulas. So there's a machinery to actually produce these numbers by Stavros and Tudor. So have a combinatorial machinery. Producing these loop invariants. So this function is also like a partition function for SL2C Chern-Simons theory, so this can be viewed in somehow some kind of combinatorial model. But it's something that you can explicitly write down from the triangulation and get the whole asymptotic expansion that's called a Jones pool. So this here is for n equal for SL2.
So the machine is for I greater than equal to 1 or I?
Well, I mean, you also get S0. That's you already have formulas for that. So, but I mean, you can also then ask in general, so for other groups, G. So then there's you can have put a question mark here. So some things generalize. For example, the Collar-Jones polynomial also exists for other. This really, you can figure that as an invariant assigned to the Lie algebra of SL2C. So for other Lie groups, there should also be some generalizations like this. And we also, this Garoufalidis-Thurston-Zickert machinery only depends on having certain equation of a certain type. So you can also produce those for other groups. Right now, we can only do SLN and PGLN, but we hope to be able to generalize at some point. So what we want is, so this goal, we don't want to just parameterize representations, we want to parameterize them in such a way that you can just directly compute these invariants over these states. So wish to that volume, complex volume, and loop invariants are explicitly computable. And we can do this for, so we will only be looking at G equals SLNC and G equals PGLNC. So So let me just summarize the setups of these two cases. There are two different types of coordinates, and they have very interesting relationships. That's some fancy language. These two groups are Langlands-Dual groups, and there should be something fancy underlying mechanism relating these two varieties. So the technology is actually very much inspired by work of Fock and Goncharov, and have also some of it has also appeared with Tudor and Goncharov, and what was the other co-author? Gabella. Yeah. And some French people, Bacheron and Talbell. Yeah. All right. Okay. So let me. So there are two different worlds. So one's Ptolemy. So this is for the group SLNC. And in another world, we have Bloom equations. Just call it Bloom. This is PGMC. So the representations we're looking at are, so let me just state some nice properties of these varieties before I start, and then after that I'll define these things. So the representations we're looking at are, let's just call this R. Oh, I should also say we also fix the topological ideal triangulation tau of that. So that's just, you have your manifold is compact, it could have boundary components, and what the topological ideal triangulation is just for each boundary component you collapse it to a point, and you get a space, and that space you choose some identification of that with some space obtained by gluing simplices. So this is into G, and it's a boundary unipotent. It just means that peripheral curves are sent to unipotent elements in Q. And this is modular conjugation. And so what we want is we want a variety. Let's call it Pn tau, and a map from Pn of tau into R. So we want an explicit variety that you can explicitly write down given a triangulation, and then an explicit map to the set of representations. And it should be such that you can just compute the invariance over here, the loop invariance of the complex volume, block invariance, whatever else we're interested in. Okay. So I'll say a little bit about the coordinates of this. So this is cut out by polynomials of Ptolemy type. So by variety, I just mean algebraic sets. So it's a zero set of some polynomials, and all these polynomials will be of the same type. They will be of the form AB plus CD equals EF. So this is a relation already known to Ptolemy. We studied that for proof that if you have an inscribed, quadrilateral is inscribed if and only if you have this Ptolemy relation between if and only if AB plus CD equals EF. That's why the name comes from. And all the equations that cut out this variety that parameterizes each representation will be cut out by polynomials of this form. And so what are the, so I also mentioned some nice properties that these are actually very computable. So the good property is that this variety is very, very nice. It has a bunch of variables and a bunch of equations that are all of the same type. And it's such that you can just plug it into Magma and get results extremely fast. You do the 8 simplex census, then on average it takes maybe 1/10 of a second to compute the whole, compute a primary decomposition in Magma of the variety. So it's like really, really fast. So we have for all census manifolds with less than or equal to 8 simplices. And we also have for not complements.
Surely the speed depends on it. And when you say
Yeah, this is for n equals 2. Exact computations are possible also for n equals 3, but for higher than n equals 3, we can only do the figure 8 knot and some components for its sister. So yeah, I should say that. So this is for n equals 2. That this is not for n. For n equals 2, this is 2. And for n equals 3, we can do all for 3 simplices, and we can do a lot of them for 4 simplices, and some for 5, but not more than that.
What do you mean by primary decomposition?
What? Sorry?
What do you mean by primary decomposition?
So primary, so Magma can split, so if you have a variety, you split it up into all components. And then it finds a Goerner basis for all these components, so that you can just read off what all the number fields are that they're defined over, compute all the values of all the Ptolemy coordinates directly from the Goerner basis.
Oh, I see. Prime ideals of the variety. Okay.
Yeah.
Are the prime ideals tend to be primitive? I mean, do you have radical ideals?
Very good question. We haven't investigated this very thoroughly, but there are very, very, very few cases where they're not radical. But we have not investigated this in any systematic way. But they very, very often are radical. So also all knots, all census knots. So this depends on the triangulation. So this is for the census one. Census knots with less than or equal to 11 crossings, and less than or equal to 15 simplices. We can do everything. We can also go up to a higher number of crossings and a higher number of simplices, but there are some of them that we can't, that don't finish. So keep them doing for a long time. So, okay, so gluing equations. I'll manage to say a little bit about the setup. So it's similar. So here we're looking at representations, all representations. So we don't impose this condition. We can, but that will require some other equations as well, which I'm not going to talk about. And again, we'll get a variety. So I don't know, we'll give people and a map. So I should say that we have this dependency of the triangulation. So if you start with any triangulation, this could be empty, for example. But if you have a hyperbolic manifold, we have some conditions that make sure that we always find at least the geometric component, and generally a lot more. Does the triangulation have if all the edges of the triangulation are essential, that's true for all the census manifolds, then we are absolutely certain that we'll find the geometric component. We're also absolutely certain that if you just start with any triangulation and do a single barycentric subdivision, you can find all representations. But of course, that's not really feasible in practice, but in theory, we can get all representations as well. Okay, so this is then cut out by polynomials. Here type. So if you're familiar with Thurston's gluing equations, you know that they can be written in this form. So product of Ci to and then Walter and here. This system has very special symplectic properties. So these are then matrices. So we have lots of equations of this type parameterized with some integer j, and the number of one cells of the triangulation. We have an equation like this for each one cell of the triangulation. That's for n equals 2. In general, it will be more. This has symplectic properties. I'll say that these are needed for the Garoufalidis. What was that machinery? That was this machinery that just combinatorially produced these SIs. They did that for n equals 2. But this machinery really works whenever you have a system of equations of this form where these matrices have certain symplectic properties. Then you can write down formulas for these SIs and compute them. Okay, so yeah, this has disadvantage though that you can't really these varieties are much harder to compute in matter. But what you can do is we have a nice monomial map relating this to that, so we can start by computing the representation into SLN and then map them into here. So if we are interested in, for example, this typing properties of SI. These loop invariants. Yeah, okay, so how much time do I have left? What? 12, 15. Okay, so I have a little less than half an hour to. So then I'll go on and say, maybe I should say a little bit before I start defining these things, say a little bit about what's the results of our computations. So we've found out that that the volume of a representation, and this is into any n. We've only actually explicitly computed it for n equals 2 and 3, and 4 for the figure 8 now, is often, and we conjecture always, an integral linear combination of volumes of hyperbolic manifolds. Take any representation, not necessarily the geometric of a hyperbolic manifold, take some other one, and you compute its volume, this is the integral of this volume form put back, you'll still get something that's a linear combination of hyperbolic volumes. And also for n equals 3, well, this space, G mod K, SL3 mod SU3, has absolutely no a priori relationship with H2. So it's still somehow kind of mysterious.
I'm sorry, that sentence confuses me. Aren't there uncountably many representations?
What?
The volume of, aren't there uncountably many representations?
Well, it's true that there can be higher dimensional components, but the volume is constant on components.
For unipotent.
Yeah.
Unipotent ones.
Unipotent ones.
Okay.
Yeah. Oh, yes, that's right. Yes. Yes.
Right, you defined volume in general.
Yes. Okay. The volume. So this is for the very good point. So this is for unipotent volume of the boundary unipotent. Very good. Otherwise, it's false.
So sorry.
These are the ones we parameterize. Otherwise, it's false. It is still true that there could be higher dimensional components of boundary unipotent representation, but the volume is constant on components.
Okay.
Okay, very nice. So the reason for this, so this is actually something that would follow from our work and the conjecture of Walter. So we prove the reason. So what we prove is that this boundary unipotent representation that actually produces an element in what's called the block group. And Walter has conjectured that the block group is generated by hyperbolic manifolds. So the conjecture by Walter. Okay. So if Walter's conjecture is true, this conjecture is also true. All right. So let me say something about how these things are defined, so that it should be possible to just go over the view. All right, the definitions. See how far I get. Hopefully I'll just have enough time to define. Okay, so the idea is that we identify the simplex of tau by with this standard simplex So this is just a standard simplex that you're all familiar with from algebraic topology. If you put n equals 1, but it's convenient to do it like this. And then we will also look at the integral points. So this is the points where all these numbers are integers or natural numbers and 0. Yeah?
I'm going to ask another stupid question.
Yes.
So when you say, in the same sentence I'm asking out, you're saying it is an integral linear combination of volumes of hyperbolic manifolds. So when you say is, does that mean up to numerical precision, or they're dilogarithms of the same numbers?
So we have actually only done it up to numerical precision.
Okay, that's
But it should be possible, at least in every concrete case, to sit and fiddle with the shapes and prove that they are actually identical in the block group. But we have not done that systematically. The only thing
but
we've
in some
done.
examples, you have.
Yeah, it's very, very few examples we have actually done that.
Okay.
Maybe one. Because in general, it's like it's really hard. There are lots of five-term relations, and actually finding those is like really. So we have only done this numerically, but the coefficients we're looking at are small, so it's not that.
Okay.
So for example, I think there's the 819 naught. This has a representation whose volume is the volume of the 52 naught minus the volume of the figure 8 naught, for example.
Okay.
And so it seems like there's some kind of weird thing going on that we don't understand. But this should also like motivate the study of these things, and the study of these varieties should be interesting in their own right. Okay. All right. So let me just draw it in some cases so we can see. So for n equals 2, this gadget here will be so there are 6 of these. So this is points here where the sum is 2. So 2 of them has to be 1. So there are 6, and these are in one-to-one correspondence with edges. So these are really just the 6 points here. I guess you can also have the corners where some of them are 2. So this is the ideal. That's 2, 3, the ideal one. That consists of these 6 points. My n equals 3. Try to draw it also with n equals 4. So each of these corresponds to some element up here of integral points. So this here will correspond to. So this is actually a subset of R4. I just projected it down to R2. It takes a little time to get used to. But this is the point 0, 2, 0, 1. And this is the point 0, 1, 1, 1. And each of these points here will correspond to a number here. And what it is really, so these, we have the 0th coordinate, the first, the second, and the third. So here the first coordinate is just the distance to the face opposite the first edge. So there's a distance 2 here. And for the third coordinate, there's a distance 1. So here, for the 0th coordinate, there's a distance 0. For the first, there's a distance 1. For the second, a distance 1. And for the third, a distance 1. So each of these points correspond to a number like this. Right? Let me just do it n equals 4. It's harder and harder to draw. I'm not going to try the 5th one.
You're just stacking oranges, right?
Yeah. It becomes uglier and uglier.
There's not just stuff on the surface of the tetrahedron, there's stuff on the inside as well.
There's the point inside. This point inside. You can't see that? So this point inside is the point where all coordinates are 1. That will live inside the simplifier. Okay, so now I'll define maybe we'll see how much we have time to define. We'll definitely have time to do the Ptolemy variety. That's the one that's kind of simplest to understand and simplest to compute. So maybe we should focus on that. We can maybe end earlier. Because otherwise I think we might have to go over, and I'd rather finish sooner. All right. All right. So we also need to. So the basic idea is that so Ptolemy relations. Ptolemy assignments. So definition. The Ptolemy assignment on delta n free is a map. We don't want things. This just means the ideal points. The vertices are removed. We don't care about those. Into C star. So what you think about is you assign to each of these dots a number, complex number. Okay. We also need another definition. A subsimplex of delta n free. This is a translate of delta 2 free with the size in R4 by an element in so this is maybe a little hard to swallow. I'll try to draw it. So what it is, you should think of it as just a copy of this gadget here inside the bigger gadget. Or think of it as copy of delta 2 inside delta n. So I'll just draw some examples of this. So here we have a subsimplex here. So you can see this configuration looks exactly like this one. And it also has 6 Ptolemy coordinates, one for each edge, just like here. And so is there another color? I'll just do another one. Maybe I'll do one in the small case. Do this one. So this is also a copy of the 6 Ptolemy coordinates. This is a copy of this gadget inside here. So here there are 4 copies, and here there will be 10 copies. Okay? Such that for each subsimplex, the Ptolemy relation is satisfied. What's the Ptolemy relation? Well, each subsimplex looks just like the n equals 2 case. So we have 6 coordinates for each subsimplex. Let's just call them now A, B, C, D, F. A, B plus C, D equals F. That's the Ptolemy relation. If you do that, you impose this, so it's clear that you have a variety, right? You have a variable for each dot and an equation for each subsimplex. So it's a variety that you can just explicitly write down. And then you can compute it, and then so this gives a variety. And I should also say that a Ptolemy assignment on the whole triangulation is just that if 2 points are identified in the gluing, of course you want the Ptolemy coordinates to be identified as well. Right? So Ptolemy assignment count. We're talking assignment non-image syntax. Respecting gluings.
How do you, there's a sign issue, isn't there?
Yeah. There, yes. So I'm sweeping that under the rug for n equals 2. There is indeed for any even n, there's a sign issue.
Okay.
But we can solve that sign issue, but that requires introducing extra signs to this equation. And these signs are governed by a cohomology class. So what you do is you find a representative of each cohomology class in H2 of M, Dn. That will give you choices of signs, and for each of these cohomology classes, you write down a Ptolemy writing and solve those.
Okay.
And if you, so the representations you parameterize for a given cohomology class are exactly the representation where the obstruction class to lifting, to a boundary unipotent lift, is that cohomology class. But that, right now, it's true that what we're doing is we're finding boundary unipotent representation in SL2. The problem is that in general, if you start with a hyperbolic manifold, then if you want to take the geometric representation, it does lift, but the lift will not be unipotent. In general, if you have one cusp, it will always take the lift of a longitude to an element with phase -2, not 2.
Oh, okay.
So if you just do these Ptolemy coordinates, like I've explained here, you will parameterize boundary unipotent representations in SL2, but in general, the geometric representation will not lift to one of those. But if you do this obstruction class business, which we can do explicitly, there will be some way of adjusting by signs so that we can get it all. So we can also get the, we can always find the geometric one. And in general, there will be, a lot more components than the geometric components. Yes?
If the triangulation is ordered, does that simplify things?
Here in this talk, I'm always just assuming that it's ordered. If it's not ordered, there will also be further signs. But it's again something that we have complete control over. But if the triangulation is ordered, everything is much simpler. So in this talk, for this to work, you have to have an ordered triangulation. And you will only get the representations that are truly boundary unipotent. So for example, if you do this naive thing for the figure 8 knot, even if you took an ordered triangulation, you will get the empty variety. You would have to get the geometric representation, you would have to fiddle with these signs. You would have to pick the obstruction class, right? So there are two obstruction classes in this case. One which is trivial, one which is non-trivial, and it's the non-trivial one that gives you the geometric representation. Because the obstruction class to lifting, to a boundary unipotent lift of the geometric representation, is a non-trivial class in H upper 2 of MDN recursion. Okay, I think I have 7 more minutes. I don't think I'll have time to do the gluing equation variety, even though my title was actually Person's gluing equations for GLN. So I think I'll just stop here.
Basically restating the fact that the longitude eigenvalue is -1 rather than 1, so for the figure 8 knot.
Yeah. Yeah. So for the figure 8 knot, this obstruction class will always be non-trivial because of this fact. But in general, there's a cohomology class that governs for a given representation the obstruction class to lifting to. For the meridian and longitude to actually lift. That's governed by a cohomology class. And for each cohomology class, you have a Ptolemy, a sign modified Ptolemy variety that you can compute. Yes?
Can you use the higher representations to detect more boundary slopes? I think. rest of the surfaces.
Oh, that I have no idea.
I mean, in SL2 you can get some, but not all, right? maybe
Good
that's
question.
not
I
four,
have
you get more.
no idea. Never thought of that. Sounds sounds like a nice question. Yes.
You lead us in thanking the organizers for a great conference.
Oh, yeah, maybe I should. I'd like to thank the organizers for a great conference.